Welcome back, folks. The topic this week is meant as a kind of stepping stone towards the so-called post-Hartree-Fock or post-mean field methods. And we are not going to go in depth when it comes to density functional theory. And one of the main reasons for that is that we have a concurrent course, which is called FYS 41110. So we need to avoid having credit overlaps. So that's one of the main reasons. However, density functional theory is actually an extremely successful theory, and it's widely used in systems where you need to deal with thousands and thousands of particles. So in material science, or if you're simulating, let's say, proteins or things like that, density functional theory, together with molecular dynamics, is actually one of the big areas of applications of these methods. Now, we are, however, going to use that as a way to illustrate and discuss different mean field methods. And the type of correlations which you will bake in, and as you will see today from today's lecture, we need in a way to have a recipe for finding the additional correlations beyond the Hartree term and what the Kohn-Sham equations give. So the Kohn-Sham equations are actually a set of equations which represent a practical way of implementing density functional theory. The big problem, however, is that you don't know how to treat the so-called exchange correlations we introduced last week. So today we are going to go through the formal theorems, the Hohenberg-Kohn theorems. So there will be a lot of text writing from my side today. There is some of the material in the lecture notes, but the Hohenberg-Kohn theorem is actually very not intuitive, but they are very easy to demonstrate, and we will go through the proofs. And then we are going to look at the Kohn-Sham equations. And tomorrow we are going to wrap up this and link that with Hartree-Fock theory and start with many-body perturbation theory, which has been one of the standard many-body methods together with FCI. So the way you can view many of these mean field methods are like kitchen items. So you set up a mean field, which then hopefully brings in some types of correlations and gives you a better basis, a better computational basis for your many-body methods. And that's why typically also FCI, even if the way we discussed it was without linking it to Hartree-Fock theory, is often called a post-Hartree-Fock method. So you run a Hartree-Fock calculation first, or a mean field calculation, that defines an optimal computational basis for you, which you think and assume is a very good starting point for your many-body theory. And then you have methods to actually elaborate the correlations. And all these methods, unless you can do a full configuration interaction, which is the exact diagonalization, then all these methods imply some type of approximation. Now, many-body perturbation theory, which we will start discussing tomorrow, is essentially a Taylor expansion around an energy, as you will see from the lectures tomorrow. And then Hartree-Fock theory, which we solve by solving nonlinear equations, is another way of rephrasing Schrödinger's equation, giving you a mean field. The density functional theory approach, in principle, is actually more fundamental, except that you don't know how to get the density. But if you have the density, then you have essentially all information about the system. So let's look at what we did last week and remind you quickly of some of the basic things. And then we are going into the theorem. We're going to prove them. Actually, the theorem is actually proved by terms in contradiction. So you will actually see that it's not that difficult to prove them. And when we've done that, although that the theorem do not give us a recipe for finding the trial wave function, they give us a recipe for making an approximation. And that approximation is the Kohn-Sham type of equations, which in a way are actually Hartree-Fock lookalikes. Okay? So this is roughly the outline of today's lecture. And many-body perturbation theory is method which has been widely popular. It is still widely popular. Many of you will encounter that as another approximation when you do many-body physics. It's often written in terms of an acronym like MBPT. And then if it's to second order, you will see a number 2. If it's to third order, it's a number 3, etc., etc. And then after that, we will probably jump into copper cluster theory, which is a widely used many-body theory in quantum chemistry, in condensed matter physics, and in nuclear physics. But let's switch over to the whiteboard. So I will essentially stay with the whiteboard most of the day, and you will find several of these theorems and also the proofs in the slides. But I wanted to actually go through this a little bit at a slower pace. So let's switch to the whiteboard. Also, before we move on, please send me feedback concerning the dates which I sent, both about the final oral examination and also the second midterm, whether these days fit or there are problems or conflicts, etc. But just let me know. Okay, so what we did last time was actually to develop an equation for the functional in terms of the density. And we actually called this functional for the Hohenberg-Kohn functional, so energy functional. And we defined that functional to be a function of density instead of the traditional path which we've had till now when we did Hartree-Fock theory. Then the energy was a functional of the Hartree-Fock wave function or a wave function. So normally we would call Hartree-Fock theory, FCI, and also many-body perturbation theory, copper cluster theory, as wave function-based approaches, because we have the energy as a functional of the wave function or the state function. Now I'm going to repeat the definition of N here. So what we had then was this given in terms of kinetic energy. So T is the kinetic energy operator, which is a functional of the density. We have the interaction piece. And this interaction piece is actually the one which is defined by the two-body interaction or more complicated interaction which we have at hand. Then there is a term which depends on the external potential. So the assumption here is that there exists a density by which you can represent the energy. And then we had, if we now, I should just say one thing, that in principle here, you should also add spin. So I'm just leaving out the spin degrees of freedom, okay? Because many of these external potentials are often potentials which do not depend on spin. So if you think back to atomic systems, like an atom like neon, atomic neon sets up a attractive external potential, which the electrons move in, and whose motion is then confined by the attraction from the atomic nucleus, which in atomic neon is given by 10 protons. And that interaction is assumed to be spin independent. But in principle here, we should also add spin. But I'm just leaving that out, okay? So I'm just leaving it out just to avoid carry with me too many variables here. And then there can be additional terms, which are often written like number 2 here. This is a term which would come from the atomic nucleus, which we often just neglect. So we would quite often invoke the Born-Oppenheimer approximation, and we would just leave that out. Now, what we did last time was actually to 1. So last time we proved that this term could be written out as a function of the density for a general wave function. Secondly, what we did prove is that the interaction piece, if we now are dealing with fermion, would have a term which comes from the direct piece, which is then just given by the density squared. But then there is an exchange part, which does not have a trivial density dependence. And we are coming back to that today because you have things like the local density approximation, which is often used as a starting point when solving the Kohn-Sham equations. Let me quickly remind you also of the definition of this quantity n of r. So we have singled out one of the particles. So in principle, this will be particle 1, but we have integrated away all the other ones, R2. And again, I'm skipping the spin degrees of freedom because in principle here, there is a summation as well over the spin degrees of freedom. But now I'm just going to skip spin. So if you go into textbooks on density functional theory, you will often see at the end, when they've done all the derivations, they say, and it's straightforward to add spin, and then we have a spin density functional. So I will just leave spin out here. And this is an integral over all the other particles, and this is multiplied with the wave function which we have of x1, no, not x1, because I'm leaving out spin. So let's just write this in terms of only the spatial degrees of freedom, R2 and up to Rn squared. So this R is then representing just the density or the expectation value of this density operator, which we defined last time. So this is just a quick reminder of what we did last time. Now, it is common to rewrite this energy functional in terms of what is normally called a functional, which depends only on the interaction and the kinetic energy, because we can assume that these, for a given type of system, are universal parts of a Hamiltonian. So it's common to rewrite this energy functional, and I'm keeping this HK, Hohenberg-Kohn, in terms of a functional, which we are going to call an f of h of k of n here, plus a term which is going to be given by the external potential, which could then be a one-body potential which attracts an electron if we are studying electrons and confines the motion of an electron. And then we include a term here which we call the exchange correlation, which also depends on the energy here. And no, sorry, this is the term. Sorry, not that one. Just a moment, I am. So this functional here is determined in terms of the interactions, except for this external interaction. So this is given by kinetic energy plus, and when we now extract the direct term, we could write that out in terms of, as we showed last time, in terms of a term which we call the Hartree term. And this is in particular if we're dealing with fermions, times n of r multiplied with n of r prime. And this is divided by the Coulomb in the relative distance. So we are setting in something like the Coulomb interaction between two electrons. You could replace this one with another type of interaction. So if you're dealing with nuclear systems, that could be the strong nuclear force, plus this exchange part. So last week, we showed that we could actually rewrite parts of the interaction piece as an integral over dr and r prime, but where we have the density. But then the exchange piece is a piece where we cannot write out a explicit density dependence. And it's often assumed that it is a local density dependence, which means that it depends only on n of r. But we're coming back to that. So all the nasty elements in the theory are actually hidden in this exchange correlation part. And if you have that one, you have essentially the recipe for finding the energy functional. So this is called the exchange correlation part. And this is the term which makes life difficult. So the term which we call F of H here, this one, is normally regarded as a universal term in the sense that it depends on kinetic energy and it depends on the interaction which we have. Then the details of the system are then defined by the external potential which confines the motion of the particles. So if you're looking at atomic neon, then for atomic neon, this part here is a universal part in the sense that it will be the same as we would have for atomic sodium, because the interaction here would be the same, the kinetic energy is the same, except that we have a different amount of electrons. However, the potential which confines the motion of the electrons in atomic neon and atomic sodium is different, because atomic neon has 10 protons and atomic sodium has 11 protons. So then the external potential changes. Okay, so we regard this F, Hohenberg-Kohn, this functional here, as something which can be seen as universal if we are dealing with a system of electrons. The only thing which will change is obviously the density here, because that density is defined by the number of electrons which are present. Okay, so in Kohn-Sham theory and Hohenberg-Kohn theory, we are normally regarding this F as a universal part of the energy functional. Okay, so one of the things which we did last time was actually to look at an example. So let me quickly remind you of that and how we can extract the equations of motion. So one of the examples of functionals which have been around on the market for 100 years, since it was introduced by Thomas and Fermi, is the Thomas-Fermi-Dirac functional. So let's just remind ourselves of that. And then what we did not do last time was actually to derive the equations of motions from variational calculus. So let me just wrap up those final details, and then we are going to attack the Hohenberg-Kohn theorems. So the example, and this is one of the very popular cases, this is the Thomas, Fermi, and Dirac functional. Thomas, Fermi, Dirac functional. And in that case, what we have is a functional where we use the kinetic energy from infinite nuclear mass, the electron gas. So this is given by a C1, and then there's an integral over d of r, and this goes like n of r to the power of 5/3. So this is the kinetic energy of the electron gas. So let me just set this up here. Kinetic energy of electron gas. That's the first term. And the constant C1, let me just remind you of that. C1 is, when we look at the expressions for the electron gas, it's actually given by 3 divided by 10, and we derived that 2 weeks ago, so 2/3. Then there is an additional term here, which is the external potential. So there is an integral of V of xt of r multiplied with the density. And then we have an additional term, which now comes from the exchange part, plus term C2, which now goes like d of r. And then if you then remember back to what we did for the electron gas, we calculated actually the exchange correlations. So this is the exchange part from electron gas. And in that case, if you look back at the equations which we had, that was a quantity which went like the density to the power of 4/3. And this coefficient C2 is then equal to minus 3 divided by 4 and 3 divided by pi of 1/3. And finally, there is an additional term, the final term, which is the Hartree term, the exchange term. For the electron gas, just as a reminder, for the electron gas, the direct term was cancelled by the electron-ion background interactions plus the ion background interaction. So for the electron gas, there was no direct term, but for a general system, what we would have then would be something like a Hartree term, where we now have an integral over d of r prime, and then we have n of r prime divided by, if this is a system of, for instance, electrons or charged particles which interact through the Coulomb interaction. So just keep in mind that you could replace this one with a general interaction here. Now, so just to remind you that this term here in the electron gas was then cancelled by the background ions, the contribution from them, and the contribution from the electrons interacting with a background of ions, a continuous background of ions. So this term was not present in the electron gas. Similarly, the electron gas does not have an external confining potential. So this term was not there, and this term was also not there. And the final energy for the electron gas is simply this term plus this term here. And these are the expectation, when we calculated the expectation value of the energy for the electron gas to first order in the interaction, this is actually what we got. Okay, so what we do then is, in order to find the equations of motion, so just keep in mind as well that if I integrate up, and this is also something which we discussed last time, if I integrate up this quantity here, the one body density, we end up with the number of particles. So we introduce Lagrangian multipliers, and then we can define a new functional where we now have plugged in the normalization condition, which is that this should be equal to the number of particles. So when we do that, we can then define a new functional for the Thomas Fermi case, where we now have a functional of the density, which is equal to the Thomas Fermi functional, which we put up, but then we have the Lagrange multipliers. So this is just the standard technique which we use in variational calculus. So the Lagrange multiplier is now mu here, and then we have to take into account that we have an integral over d of r, n of r, which we are constraining to be equal to the number of particles. So I'm just setting up some of the basic equations which you would typically start with when you use the calculus of variations. So then we are going to look at small variations, and we can then use the Euler-Lagrange equations to find the equations of motions. So I don't know if you remember, but some 4 weeks or 5 weeks ago when we discussed Hartree-Fock theory, we went for a simple example of a one particle problem in 3 dimensions. And then we put up the energy, we varied the wave function, and then we got the equation of motion from the energy, which was, surprise, the Schrödinger equation. And if you do the same with Newtonian mechanics systems, when you set up the Lagrangian with kinetic energy and potential energy, when you then apply the formalism of variational calculus, you get Newton's equations of motion. So it's an extremely powerful way of extracting the equations of motion. So we're not going into the detail of variational calculus, but we are going to then look at small variations. This is basically the standard technique which is used. You look at variations to order delta n. So these are the variations which we are looking at in density. Remember, then we did this for the wave function based method, which led to Hartree-Fock theory. Then we were looking at a variation in the single particle wave functions. Now we just look at a variation, a tiny one, in the density. And then what we want then is obviously that this difference, which now expresses an integral over all the possible paths which we can take, given a small perturbation. Then we will have this functional TF here, which is now a function of n over r plus some delta of n over r minus, and then we have the omega Thomas Fermi as a function of density here. And we want to drive this difference to 0, to first order delta. Now, if I do that, if we now calculate, I'm going to set up the equations in a little bit more sloppy way, because we are now going to look at the functional derivatives. So if I take the kinetic energy term, then what I'm going to get then, if you look at the term, we have here we have 5/3. So that means I will get a term here which goes like C1 multiplied with 5/3. And then it's multiplied with density to the power of 2/3. Then what I'm going to do now is simply to set up an equation here in terms of a potential V of R minus mu. And this is multiplied with a delta N of R. So what is this V of R? So this V of R is actually going to be given by my external potential, because I'm taking the functional derivative with respect to delta N with it NR. And if I do that for the term which you see here, for the first term, this one, then this is pretty simple. That just gives me external potential. Then for this specific term, I will get a factor of 4 divided by 3 times C2. That's for the exchange part. And then for the Hartree guy here, I'm going to have 2 densities. So that will give me density multiplied with 2 divided by 1/2. And then I just get density. But I'm going to write this one as the external potential plus, without writing it out in full detail, plus Hartree plus this V exchange. And my V exchange here is actually going to be equal to this term, C2. It's going to contain 4/3 multiplied with the density to the power of 1/3. So that defines my potential. And if I then require that in order to satisfy the equation here, that this equation here should be equal to 0, in order to satisfy that one, it suffices to actually look at the equations which you have in here. And that gives us simply the equations of motions. So what I'm going to have when I plug in everything here, I'm going to have 1/2 times 3 pi squared to the power of 2/3 multiplied with density to the power of 2/3 plus this potential V of R equal to 0, equal to mu. And mu plays the role of the energy. And what you have then is a term first. So this term is actually the kinetic energy in terms of density, kinetic. This is then the potential energy. And this plays the role, this Lagrange multiplier is then identified as the energy. And what you have here is then the equations of motions. Equation of motion. So later, when we are going to derive the Kohn-Sham equations, we are going to use operational calculus again. And then we will get a new equation of motion, which will be a Hartree-Fock lookalike. And then with that one, we can actually solve the problem for the single particle orbitals. But that's something which will be in the coming here. So this was just an example, and this was partly a reminder from what we did last week. The thing which we need to discuss now in more detail are actually the famous Hohenberg-Kohn theorems. And there are 2 theorems, and each one of them has a corollary. So we're going to look at the theorems and also look at the proofs of the theorems. Okay, so theorem 1. So I'm going to write a lot in, I'm simply going to write a lot of text here, if that's okay. So theorem 1 states the following. So for any system of interacting particles, there is actually, for interacting particles, in moving in an external potential, and this is the potential which we called V of X, V external. Then the external potential is determined uniquely, except for a constant by the ground state single particle density. So let's just write this down. So in an external single particle potential V of xt, then the external potential is uniquely determined except obviously for a constant by the ground state single particle density. So if you know the single particle density, then that defines uniquely the external potential. So keep in mind also that we have assumed that this energy functional has a part which is universal, which then contains kinetic energy plus the interaction energy. And the interaction energy is universal for a given set of particles. So is uniquely determined, so everybody have written that down, is uniquely determined except for a constant. By the ground state of the system, by the ground state density which I'm just going to call N0 of R. So this is actually, keep in mind that this is the single particle density. It's not the many-body density. But just keep in mind that this was obtained by integrating out all the other particles except one. So that tells you, the single particle density tells you where the particles are located with a given probability. So keep in mind that this is the single particle density. And you will see that this connection with a single particle density gives us a very nice link with Hartree-Fock theory, as well as the approximations which are represented by the Kohn-Sham equations. Now, there is a corollary here. So let's just put that one up. And let's just call that corollary 1. So what that says is that since the Hamiltonian is fully determined, except for a constant shift of the energy, it follows that the many-body wave function for all states, both the ground and excited states, are then determined. So since the Hamiltonian is fully determined, except for a constant shift, or a constant shift of the energy. So we can always add a constant shift. Then it follows that the many-body wave functions for all states are determined. That the many-body wave functions So this requires a little bit more labor, but you can actually, through different methods like equation of motion methods, if somebody gives you the ground state of the system, you can then define all the excited states as well. So it follows that the many-body wave function functions for all states. It's determined. So that means that all properties of the systems are completely determined when you know the ground state density. This is very important because if you have the wave function, you can calculate any transition. You can calculate any expectation. You can look at transition probabilities. If you're looking at decays, excited states which decay to a lower line state or to a ground state, you can then calculate the transition probabilities. And then you can relate some of these experiments, like if you're doing nuclear physics, it's very popular to look at the beta decay or to gamma decays, where then you have an excited state which decays, for instance, to the ground state. And you can then calculate the related time or lifetime of a given state. And these are things which you can extract from experiment. So if you have the ground state density, you can then actually calculate all properties of the system. Obviously, this is the time-independent problem. There is a whole field of research which is called time-dependent density functional theory, or time-dependent theories where you deal with the dynamics. So this is one thing which we don't touch upon in this course, the time dependence of a system. So we are mainly focused on time-independent properties, which means that we're looking at correlations without involving time. So if you wish to study time dependence, that's another 10 credit course. Okay, so theorem 2, that's another theorem here. Right? We could actually summarize this Hohenberg-Kohn theorem 1. So we could have a ground state density like this, and then we have an arrow which points to this external potential. So if somebody gives us that, and the density which we have here, that density can then be used to find the, so if somebody gives me the ground state of the system, I can use that one to define the density. That defines my potential, which in turn can then define the excited states or any state of the system, and that feeds back to the psi zero case. So there's a kind of circular statement here. So theorem 2, on the other hand, goes as follows. So let's just write down all these theorems first. So the theorem says that the universal functional for the energy in terms of the density can be defined, and it's valid for any external potential. For a particular external potential, the exact ground state energy of the system is the global minimum of the functional. And the density that minimizes the function is, or the functional, is actually the ground state density. So let's just write this down. So a universal functional, and then we should take a break when you've written down all this stuff here. A universal functional for the energy. So when I say the universal functional, this is actually this function F, which we defined, which contains the kinetic energy plus the interaction energy, and not the external potential, okay? So for a universal functional for the energy, E of n. So keep in mind here that what we have when we say universal, it is actually this quantity here. That was defined in terms of kinetic energy and the potential energy. That means the interaction energy. So for a universal functional for the energy, in terms of the density, so it's a function of the density here, so a universal functional for the energy in terms of V can be defined, let's just wait a little bit so everybody has the time to write it down. So the theorem says that the universal functional for the energy in terms of nr can be defined and it can be defined and it is valid for any external potential which we have labeled V of xt. And for a particular V of xt, the exact ground state, state energy, the exact ground state energy of the system is the global minimum, of the functional, the energy functional, and the density n of r that minimizes that function or the functional is the ground state density. And so, and the density nr that minimizes E of n is the ground state density. Which we called N0 of R. Now, there is a corollary to the statement here, and that corollary says that the functional alone is sufficient to determine the exact ground state energy and density. In general, excited states must be determined by other means. So the corollary simply says that the functional alone is sufficient to determine the exact ground state energy. So let's just state the corollary and then we take a small break. So the functional E of n alone is sufficient to determine the exact energy, the exact ground state energy, and density. So after the break, we're actually going to look at the proofs of these two theorems. So the proofs are actually very general and simple, and the theorems give us general statements about a many-body system. So if you have the density, it means that with the density, you can then calculate all properties of a system. So this is an extremely powerful theorem, in particular theorem number 1, except that if we had the density, there would have been no point in us meeting on a weekly basis, because we have to make approximations to get the density. So if we could solve the problem, I guess this course would have been totally redundant. So let's now look at the theorems. So the theorems are generic theorems about the system, where we now, instead of expressing the energy as a function or functional of the wave functions, we're expressing the energy as a functional of density. And with that, you can actually make pretty unique statements about the density and its connection with external potentials. And that's extremely powerful. However, if we want to find this density, we have to make approximations. Or stated differently, if you cannot answer the questions, you ask another question. That's essentially what we end up doing. We'll take a small break. Is that okay with everybody? So feel free to ask questions anytime. So what we're going to do now is to go through the derivation of the theorems. And let's take a look at the first theorems. And the proof of the theorems actually often, they're actually pretty simple. And what we have, if you look at the first theorem, what we have then is a density as a basic variable. So let's look at the proof of theorem 1. So we have defined density as a basic variable. So n of r is now assumed to be as a basic variable. So let's assume that we have two potentials now. And to each of these potentials, there is the same density. So if you look back at the first theorem, let's just quickly remind ourselves of that one. So what the first theorem says is that for any system of interacting particles in an external potential V of x, the external potential is uniquely determined, except for a constant, by the ground state and density. Okay, that's the first theorem. So let's assume now, so since we have now said that the density is a basic variable, let's now suppose that we have two potentials, two external potentials. Suppose we have two external potentials, and we label this as 1 and the other one as 2, obviously. And they differ by more than a constant. And they differ by more than a constant. Differ by more than a constant. So this is an assumption which we are making, okay? And what we're also assuming now is that these two potentials lead to the same ground state density, okay? So, and they lead, well, let's just wait a little bit here so everybody has been able to write it down. And they lead to the same ground state and density. So let's just write that. So I'm just saying, suppose we have, I guess it's this one which is a little bit unclear. Yeah, and V of x, and they differ by more than a constant. So this is just an assumption which we are making. And we're also saying that the two external potentials lead, they actually, and that they lead, so the two potentials, and they lead to the same ground state density. and 0 of R. So this is an assumption we are making. And then we are going to show now that this leads to a contradiction. And the contradiction is the proof of the theorem. So the two external potentials obviously represent then or define two different Hamiltonians. So keep in mind that the Hamiltonian has a universal part, which is the kinetic energy plus the interaction. So what we have then, since we have two different potentials, we will have a Hamiltonian 1, which is going to be kinetic energy, which I now write this in a more dense way. And then we have external 1. And then there is going to be another Hamiltonian, H2, which has the same kinetic energy, the same interaction between electrons, for instance, but now a different potential. And obviously, each one of these, this one leads to a wave function, psi of 1. And this one has a psi of 2 here. So they have two different ground state wave functions, which are hypothesized to have the same density. But we assume now that psi 1 and psi 2 have the same density. So what we can assume now is that since, so this psi 1 and psi 2, they are the ground states of the system. So I'm just going to put a GS here. So GS stands for the ground state. So when I use the shorthand GS, that is always the ground state of the system. So they have two different ground states. And what we are doing now is that I can define the energy 1, which is equal to psi 1 of H1 of psi 1. So that's the ground state energy. Now, what I can assume then is that this psi 2 is not the ground state of H1. So I'm going to assume then that this is smaller than psi 2, but with the same Hamiltonian. Sorry, psi 2 here. So I'm now assuming that the ground state of H1 is psi 1. And that means that if I take another function and calculate that expectation value, I'm assuming that this expectation value has to be give an energy which is larger than the ground state. So the ground state is the lowest possible one. Does that sound plausible? So these are just assumptions I'm making about the system. So that strict inequality follows if the ground state is non-degenerate. So keep that in mind. So GS is non-degenerate. This is pretty common for many, many systems, but I can have systems which are degenerate, so that they have more than two energies which have the same value and different wave functions. So this is an assumption which we are making here. So there's a unique ground state energy and ground state. So if I now look at what I've done, I can now rewrite the term which I had with psi 2 here of H1 of psi 2 here. This is the same as, I'm just manipulating these equations. And then I have H2 of psi 2 here, plus, and then I have psi 2, and then I have H1 minus H2. So I'm just manipulating this equation here. This is something which I then can rewrite in terms of the external potential. So now keep in mind that the kinetic energy and the potential energy are quantities which are the same for both Hamiltonians. So this is something which I then can rewrite as an energy. So this energy which we have here, this one, is nothing but E of 2. So I get this as E2 here, plus. And the only thing which distinguishes the two Hamiltonians is actually a quantity which is d of r. And then I have a V external of 1 minus V external of 2. And there's another thing which we have to pay attention to is that we have assumed that these two functions have the same ground state density. So we are going to show that that leads to a contradiction. So we have an N0 of R here. So this term which you see here follows simply from the fact that we have made an assumption about the ground state energies and densities. So this term here, this one and that one, they have the same kinetic energy and they have the same interaction energies. So the only thing which survives then when we look at that difference is actually this term here. So on the other hand, if we consider this E of 2 in exactly the same way, so let's just, on the other hand, so this is the first equation. On the other hand, if we now consider E2 with the same kind of way, this means that we just need to interchange the superscripts 1 and 2 in the equations. So if we now, if we consider E2 the same way, in exactly the same way, then we find the same equation, but with the superscripts interchanged. Then we find, and I'm going to put some labels on this. I'm just going to call this for asterisk 1. And then I'm going to have the next equation. If I do that, what we will find is that we have E of 2. So if you look at the equation which we have here now, this equation here, this one, is an equation which is smaller than E1. Because you see here that what I did was to write out this one. So this is assumed to be smaller. So in a certain sense, we can actually rewrite this one, this equation here, and that is larger than E1. If I interchange these two indices, what I get then is that E2 is going to be smaller than E1 plus a d of r. And then I have a V x2 here minus V external of 1 multiplied with the ground state density, which we are assuming is the same for the two states. So if I add these two equations, so let's just give that a label. So adding 1 and 2 leads to a contradiction. Leads to E1 plus E2 being less than E1 plus E2 here. So that's clearly a contradiction if we now assume that the two potentials, which are different by more than a constant, correspond to the same ground state density. So if we look back at the theorem which we stated, theorem number 1, so if we look at that one, what we say now is that for any system of interacting particles in an external potential V of x, the external potential is uniquely determined, except for a constant, by the ground state density. So what we did now was to show that if we have the opposite, then we get a contradiction. And that establishes the proof for theorem number one. So that means that there cannot be two different external potentials which differ by more than a constant, which give the same ground state density, and which give rise to the same non-degenerate ground state charge densities. So that means that this n, which we have now, uniquely determines the external potential to within a constant. So the consequence of this is that if we now look at this theorem here, what we can say then is that the density n of r, the one-body density, uniquely determines the external potential to within a constant. To within a constant. Note that what we have done now does not give a prescription for finding this density. We are simply just stating that given such a density, that uniquely determines the external potential. Because if we suppose the opposite, then we end up with a contradiction. So you're showing the theorem by demonstrating the contradiction. So you demonstrate it by showing the opposite, that if that's not the case, then you end up without contradiction. Okay? Because in the proof here, what we did was simply now to assume that these two wave functions correspond to the same density. Okay? So let's look at theorem 2 then. And let me find my stuff here. So the second theorem. So proof of theorem 2. So since all the properties which we have, such as the kinetic energy, are uniquely determined by this density, when that is specified, then each property can be seen as a functional of the density. So since all properties, so let's go back to the theorem, by the way. So just because we wrote down the theorem before the break, so it can be good actually to look at the theorem again. So we say that the universal functional for the energy in terms of nr can be defined, which is valid for any external potential, V of x. And for a particular V of x, the exact ground state energy of the system is the global minimum of the functional. And the density n of r that minimizes the of n is the ground state density. So this is roughly what the theorem says, that for a particular Vx, the exact ground state energy of the system is the global minimum of the function. So let's look at how we can attack that theorem. So what we have is that since all properties such as kinetic energy, potential energies, etc., such as kinetic, potential, etc., kinetic, potential energy, etc., are uniquely defined if this quantity n of r is specified, if n of r is specified, then each property can be seen or can be viewed, then each property be viewed as a functional of n of r. So what we have then is that the energy, so let us quickly repeat some of these things. So we have the energy EHK, the Hohenberg functional, is then a function of the kinetic energy, which is a function of density, plus the interaction part, which we are treated as a universal part of the Hamiltonian here, plus this term, which is now defined by the external confining potential multiplied with density. And then I'm just going to put in parentheses here additional terms which we are going to leave unspecified, or which we are going to drop out in the discussions, such as the electron-ion interactions or the electron-atom interaction, etc. So we just leave that one out, and we're now looking just at the electronic degrees of freedom. So I'm going to put a label to this equation because I'm going to refer to that later. And this equation has 3 stars, because in the previous case we had 1 and 2 stars. So this is equation 3. So what we're going to do now is to consider a system with a ground state density N1, and that corresponds to an external potential V1. So let's now look at that specific case. So we have an N1 of R, and that density corresponds to an external potential, V external 1. So remember now that the Hamiltonian contains a universal part plus the external part, which is system specific, if you're looking at, let's say, only electronic degrees of freedom. And then if you then add this external potential and you solve Schrödinger's equation, that gives you one given ground state. If I change the external potential, so instead of having an electron in neon, I have an electron in sodium. That is a different system. And then that obviously leads to a different ground state, obviously. So what we are going to say now is that this energy, there is an E1, which then is simply given by psi1. And then I have this Hamiltonian H1, which now contains this external potential, like that. And then what I'm going to do next is to consider a new density, which I call for N2. So then I consider, and then consider then an N2 and a psi2 here. Now this psi2 is obviously not the ground state of this H1. So that means that this E1 here is equal, which is equal to psi1, which is repeated here, of H1, and psi1 here, that must be larger than psi2 of H1 of psi2 here. So the energy then, which is given by this equation with the 3 stars, so the energy, so this has to follow because psi2 is not the lowest lying state of H1. This is a different one. And we have assumed that N1 and psi1 are the ground state densities and ground state wave functions. So that means that if I have another one which corresponds to another density, then clearly this energy here has to be different. And we have assumed that we have a non-degenerate ground state. Okay? So what that means is that the energy which you have, which is given by this equation, which we label with 3 stars, of the Hohenberg-Kohn functional evaluated for the correct ground state density is indeed lower than the value for any other density of the energy given by of the HK functional is in terms of, no, wait, I have to, for the energy given by of the HK functional evaluated, I have to write off correctly what I evaluated. Weighted for the correct ground state density N0R is indeed lower than the value just correct things a little bit so it looks a little bit nicer here than the value which we obtain for any other density. Value for any, I'm not going to come back here, for any other density N(R). And that follows simply from the variational principle. So the second theorem is actually pretty easy to show because that is a consequence of the variational theorem. So what we are saying then when we replace that wave function, so we assume that these two quantities here correspond to that specific wave function, and this is the lowest lying state. If I consider any other one, then the variational principle tells me that this quantity has to be larger. And that means that the energy which we calculate with this functional here, using variational calculus, is an energy, when it's evaluated for the correct ground state, is indeed lower than the value which you get for any other density. And that simply follows from the usage of the variational principle. So the second theorem is actually pretty straightforward to see and understand. That is just an application of the variational theorem. So the two theorems, they actually give us a very general set of statements about a many-body problem. So if I can specify the external potential, then there is a unique density to that one. And then if I have such a unique density, then theorem number 2 follows that that is the density which represents the lowest lying state of the system. So the problem, however, is that these theorems, they don't give us any help in solving the equations. And that's where the Kohn-Sham equations come. So the Kohn-Sham, it's called an auxiliary system because we impose an additional condition on the wave function. And that additional condition which we are going to impose on it is that we can write the wave function of fermionic systems like a Slater determinant, which is set up by single particle states. If we do that, then we can actually derive a set of equations which are Hartree-Fock lookalikes. But instead of involving the single particle wave functions, they're going to involve the densities. But at the end, we end up with equations which are pretty similar to the Hartree-Fock equations when we are going to solve things numerically. So as I said, these two theorems give us general theorems about a many-body system as a function of the density. If we have split the Hamiltonian in a universal part and an external potential which confines the motion of the particles. Does that sound okay? So I'm trying just to repeat some of the things because it takes time to digest the way of thinking. So you have a Hamiltonian which contains a universal part, which is given by kinetic plus the interaction energy. It's universal in the sense that they take the same form when they act on the same type of particles. Then there is an additional potential. This could be a harmonic oscillator. The particles move in a harmonic oscillator. That will give us a given ground density, ground state density. If I have another external confining potential, I will obviously have a different wave function. So if I have particles moving in a harmonic oscillator trap, then the wave function, the single particle wave functions, will be harmonic oscillator lookalikes. If it moves in a potential like the Coulomb interaction from the atomic nucleus, it will behave like a hydrogen-like solution, which goes like the exponential with argument minus r. So different external potentials will give us different wave functions and different ground state densities. And what the theorem says, theorem 1 says, is that this external potential uniquely defines the density. Then when you have this density, that according to the second theorem, then what that says is simply that universal functional of the energy in terms of the density can be defined, which is valid for any external potential. And for particular external potential, the extra ground state energy of the system is the global minimum of the functional. Okay, so this is very fine, but it doesn't give us a recipe. And this is where the Kohn-Sham equations come in. And you have lots of varieties here. So this is a huge field, especially since there are there have been tons of investments in material science on developing density functional theory. So many research groups, they actually use license-based software for density functional theory. So there is one which is very popular, which I assume that some of you have been using, which is called VASP, V-A-S-P. And like the university here pays a license of 100,000 Norwegian kroner per year to use that software. And these are softwares which are extremely flexible. You can adapt them to many, many different systems. So if you're looking at, let's say, point defects in semiconductors like silicon carbide, you can fine-tune the density functional equations to that specific system. You can pick another system like a protein, and then you can tailor the boundary conditions, etc. So you get a one-body density from that type of system. And then you can use these in more refined many-body calculations. This is often called embedding. So you use a simpler set of equations to extract a one-body potential and one-body wave functions, which you then plug in into your more fancy many-body method. So in a certain sense, these methods, these mean field methods or mean field-based methods, are methods which you can perceive as a kind of kitchen item, which then give you a computational basis which may be more suitable for that specific system. And the Kohn-Sham equations is actually the practical recipe. There's much more to the picture than what I'm going to tell you, but that's because these equations, they have led to tons of new developments where you can include higher order corrections to the exchange correlation part. But let's now look at the Kohn-Sham equations and look at the basics here. So they actually rest on two assumptions. So what we are doing now is to replace one problem with another problem. But they rest on two assumptions. They rest on two specific assumptions. One, the exact ground state can be represented by the ground state density, by the ground state density of another system, of an auxiliary system, of non-interacting particles. So if you now think back to what we discussed earlier with Fowler's theorem. So if you think of a system of non-interacting particles, that could be a Slater determinant. That is the solution to the non-interacting problem with a given external potential. So let's just take that as a small intermezzo before we list the second point. So the example which we have met here is a system where we now have an ansatz phi, and I'm not putting a subscript on it because this could be any. And then we have x1, x2 up to some xn. And this could be, I'm not saying that it is, but it could be the standard Slater determinant, which we have dealt with. So we have a single particle state 1, we have x1, phi 2, so the particles in the columns, and phi of n. So these will be the states up to the Fermi level. And this continues till phi 1 of xn. And now these x's contain both spin and the spatial degrees of freedom. And xn here. Now, one of the exercises we had very early in the semester, and which we also went through last week, is that then the single particle density, n of r, can then be written out as a sum over I equal 1 up to n of these states phi of I of r. So let's just write x here because we are putting in the spin degrees of freedom as well. And you can see that immediately if you have a basis of orthogonal functions, because here we have now assumed that this phi of I and phi of j is equal to delta ij. So this is a basic assumption which we made when we constructed such a Slater determinant. In that particular case, what we have now is that the one-body density is now simply a function of the non-interacting problem. Keep in mind then that this solution here, when you have such a Slater determinant, that was the solution to the Hamiltonian part, which we call H0, which was kinetic energy plus an external potential. So that means that now we are making an assumption that the ground state of the system can actually be represented by the ground state of an auxiliary system of non-interacting particles. So what we have seen before from Fowler's theorem is that this is not true. So this is an approximation. Because Fowler's theorem says that we can write any Slater determinant as a linear combination of different one-particle, one-hole excitations, period. It does not include higher-order correlations. So this system here, the ground state is not given by a single determinant, period. But this is an important assumption which is being made in order to be able to solve the problem. So as I said, if you cannot solve the problem, the full problem, you replace it by another problem, which then obviously becomes either an approximation or the exact way of solving it by perhaps some easier means. Okay, so that was the first assumption. Then there is an assumption 2 here, which also kicks in. And that is that this Hamiltonian is chosen to have the usual kinetic energy and an effective local potential. So the call this an auxiliary one, this auxiliary Hamiltonian, which corresponds to that wave function. The auxiliary H is chosen to have the usual kinetic energy and an effective local potential in the density. So we're coming back to what we mean by a local potential in the density. And effective local potential. So let me emphasize that, because I need to explain to you what we mean by a local potential. By an effective local potential, which we will just call V effective of X. Now, let me give you a small reminder here. And this is where we will stop the lecture today. So a parallel, this is the Hartree-Fock potential. So if you think of the Hartree-Fock Hamiltonian, you can think of that as an auxiliary Hamiltonian, where we had H Hartree-Fock, which was then given by the kinetic energy, T, plus this term U external. So I'm just writing this a little bit different. And we label this one as an operator H0, plus a U Hartree-Fock. And when we calculated the overlaps here between two single particle states, that will be given by P of H0 of Q plus the Hartree-Fock potential, which then had a summation over states below the Fermi level. And then I have my P, my J, my V, and then I have my state Q and J anti-symmetrized. So this thing which you see here now, this one, plays the role of an effective potential. So what we say then when we do Hartree-Fock is that effectively the states P and Q see a correction to their motion due to the other particles below the Fermi level. So Hartree-Fock in itself is actually us modifying the motion of a particle due to an external potential and kinetic energy by the effect of the bystanding particles. So what we could say then is that Hartree-Fock then introduces an effective potential where a particle sees a medium set up by all the other particles. And that corrects the motion of the particle. So Hartree-Fock, in a way, is an example of such an auxiliary Hamiltonian, which then gives us a set of single particle wave functions, which we then could use to define the Hartree-Fock ground state function, which then would be a Slater determinant if we're dealing with fermions, a Slater determinant which consists of this basis here, which is an eigenbasis of the Hartree-Fock Hamiltonian. So the Hartree-Fock theory in itself is a kind of parallel to what we are going to set up tomorrow, which means also that this effective potential is in a way going to mimic the Hartree-Fock equations, except that Hartree-Fock theory has the interaction to only first order. It contains the direct term and correlations due to the Pauli principle due to the exchange term. So there is a correlation part. So if you think back to that XC term, which we had in density functional theory, where X stands for exchange and C for correlations, Hartree-Fock theory contains the correlations to first order in the interaction. So there's a clear parallel here. And the Hartree-Fock and the Kohn-Sham equations are actually equations which in spirit represent much of the same philosophy. And the Hartree-Fock Slater determinant is not the solution to the full many-body problem, but it represents a good approximation. And if I use the Hartree-Fock basis, so if these single particle states are Hartree-Fock wave functions, then this would apply and this would apply. So tomorrow, what we are going to do then is to use the variational principle and the Kohn-Sham, the Hohenberg-Kohn functionals, and set up the Kohn-Sham equations. And that's where we're going to stop today. So the first part of the lecture tomorrow is to fulfill the density functional theory part, and then we move into post-mean field methods, like many-body perturbation theory. Okay, so I hope I've been guiding you so you see the wood for the trees. I hope so.